Okay. Okay, recording has started. Okay. So the topic we're going to cover today is um, like Intel software guard extensions, SGX. So I think many of you have heard this. Okay, so we will go over the problems they try to solve and the main techniques. So this is the protection we know we have learned so far, right? We spent quite a bit of time in this course to talk about the software and the operating system security. Yeah. Um, we know the processor provides the different protection levels. In traditional Intel's processor, we have four levels of privilege, range 3 to range 0. And later on, we talk about a virtual machine, and the virtual machine will have two levels in range 0. There's root mode and non-root mode. Some people call root mode like range -1. So we have actually 5 levels of protection, right? So we spend quite a bit of time to discuss the security features in operating system and in processors. Yeah. So the kernel of the operating system will have the privilege, their privileged code in the privileged mode. The applications runs in the normal user mode, has less privilege. So operating system can provide separation, isolation. So the apps, one process cannot access the data that belong to other processes. And so there's war between processes. So of course they have some ways to communicate. So we learned like inter-process communications. So applications can talk to each other through shared memory, through uh, uh, pipe, through files, and some other um, approaches provided by operating system. So those communication methods are managed by operating system, right? So application cannot freely access data belonging to other processes or belong to operating system. So there's a war between them. So everything works nicely, all right, until operating system is compromised. All right, then that is bad. Yeah. So we talk about the like, principle of least privilege. So operating system would give least privilege to certain applications or certain processes. So even those applications are compromised, the damage can be controlled. But if somehow the application, the attackers can get into the privileged mode, then everything goes wrong. Okay. Well, bad thing will happen. Right? So there's no isolation, no war between applications. So that's the problem. That's the problem. The operating system is complicated. The many lines of code, and the many people work on the operating system. I accidentally watched a video a couple of days ago talking about the React OS. That's a open source project uh, that that was designed to replace Windows. The project started about 20 years ago, or even earlier, 25 years ago. At that time, they want to replace Windows, have a similar operating system, have a binary compatibility with Windows. That was many years ago. But even now, they couldn't have like something comparable to Windows 20 years ago. So it's very complicated. Uh, Microsoft had millions of engineers working on Windows. So you can see the level of complexity in the developing operating system. So there will be bugs. So how can we prevent those like catastrophes? Right? And how do you know so no malware has compromised the operating system? So we talk about like measured booting and the secure booting. Measured booting, you can do it with TPM. You can with secure booting. You can check the code, the operating system loader and the other modules before you run, right? So the code can pass all the checking, but still there could be bugs in the code. Okay? So when you check the code, it works well, right? But because of the bug, the attackers can still get into the privileged mode, and it is very hard to detect. You know, the rootkit and the BIOS kit, whatever kit can get into the more privileged mode, can get into the early stage of the booting process. Right? So that is hard to detect, and it's very hard to check. So the merit boot, secure boot will not solve all the problems. This is from the point of view of like you have a computer that attackers may try to break into the system. There another scenario is you do not own the computer. You get a service from third parties, from Amazon, Google, Microsoft. They all provide um, services. You can rent a virtual machine, right? And there are many providers, like hundreds or even thousands of providers. You may not want to get uh, service from like big companies because they're expensive. Right? So many of you will get deals. Okay, so small companies provide a very cheap service, like $1, you can get a VPS. $1 per month, you can get a VPS. Right? So how do you know that your data are, are good with those companies? You may run some application processing confidential data or like a private data. It may not be very important, but you don't want other people to know. Right? So how do we know that your data are good with those companies? Right? Think about those scenarios. You don't know the hardware. You don't know the operating system. Okay? Because typically you just use the image provided by those companies. Right? You could upload your own image, but how do you know the image you uploaded are not modified? So basically, you don't know the hardware, you don't know the operating system, and you don't know what they're going to do with memory, with the hard disk. Right? So you don't really know everything. Okay, you just log into the system and you start to process data. Right? So that's the problem. Right? People are worried about that. Especially you have a secret you're going to get rich in a couple of years, right? So you have a brilliant idea about some product, you don't want anyone else to know that. So that's the issue people want to address. So Intel has a way and AMD has a way. So, but in today's session, we only focus on Intel's method. Intel calls it the software guard extension. So most of the time, if you just say SGX, and then people in architecture and the security field should know the meaning of the word. Actually, this was introduced a few years ago. So the problem they try to solve is this. So even the hardware, the operating system cannot be trusted, you can still protect the secret in applications. So they put some features in the processor and establish a trusted environment called enclave in application. So as a result, direct advantage from this is if you get a service from some parties you don't really completely trust. So for example, you don't trust Amazon, but you can still know that the whatever secret you processed, computed on the remote server are secure. Amazon cannot know the contents, know the secret. That can also prevent, okay, the technology can also prevent many attacks we have discussed. So the security parameter assumed in SGX is the CPU. Okay, so basically Intel says the hardware of the PCB, the motherboard cannot be trusted, the memory may not be able to be trusted, and the operating system cannot be trusted, right? But if you trust our processor, then your secret is secure. Right? So the assumption is the processor itself is trusted. You can trust the Intel. So the security parameter is the CPU package. Everything outside may not be trustworthy, but inside CPU, okay, you have a code and the data in clear. Okay, if that security assumption is not true, then of course you won't have any protection. So suppose this is the package in the CPU, the processor. You have a cores, you have a cache, and you have other circuit inside that. Right? So everything within the blue wall, probably I should change it to red wall. Within this wall, within that box, is clear. Is assumed to be secure. And everything outside is not secure, including DRAM. There is connection between DRAM. Remember the code boot attack, right? The attackers may be able to reduce the temperature and examine the content stored in DRAM. So that is the attack on the memory system. With SGX, the data you want to protect are encrypted when they're stored in DRAM. There's memory bus to communicate between the core, the CPU, the processor chip, and the DRAM, but the data on the bus are encrypted. And so some people may put a probe there to look at what the data are transmitted on the bus, but they can only have ciphertext. They cannot decrypt it. So the data in memory are protected. With SGX, the application want to protect the data, can establish a secure environment. We learned a moment ago is called enclave, right? So this is the memory view, the layout of the memory space used by a process. And we know the application can put the data in the lower end of the memory space, then the data and the stack and many other stuff, right? So higher end is reserved by operating system. The enclave is within this virtual memory space. So inside the enclave, the secure environment can have a code, it can have a data, and the multiple multi-threading is supported. So you can have multiple threads running in this secure environment. And there's data structure to manage the threads. It's called TCS. I think it's a thread control structure. So there could be multiple threads in the secure environment. So this is the enclave. So everything inside this, enclave is supposed to be secure. Yeah. But the entire process is managed by the operating system, and the application may not trust operating system. So how do they do that? Right, that's the question. How do they do that? First, we look at how data are stored in memory, because we learned the data, the data you want to protect are encrypted in memory, right? And the operating system should be able to see the data, right? Actually, to prevent the operating system to steal the data, the processor reserved some physical memory. Right? So operating system do not have access to that part of the memory. Right? So when the system boot up, you can set in BIOS. Yeah? You can reserve certain physical memory, certain region to be used for enclave, for secure storage. Yeah. So it's called the processor reserved memory. This will be used by enclaves. Enclaves will be created by processor, not by operating system. But the operating system will participate. Yeah. We're going to see how this how this is done, and we're going to see the flow of creating enclaves. Yeah. So part of the memory is reserved by the processor. Yeah. You can set in BIOS or firmware how much memory you want to reserve for enclave. Actually, the part of the memory used for enclave is actually so small. I think it's about 128 megabytes. So when application want to create like enclave, it will use some instructions, processor instructions to create enclave. Right? Enclave are divided. Those processor reserved memory are divided into pages, and these pages can be allocated to different processes. So each time a page is allocated to a process. So this enclave page cache are divided into pages, each 4K 4K bytes. Also, there's enclave page cache map. Store some mapping between the virtual address and the physical address. Yeah. This is not used for translating virtual address to physical address. And we know the page table is used for that purpose, right? But the page table is managed by operating system, and the processor does not really trust the operating system. So it has its own mapping here. So after the page table, the translation with page table is done, processor also do some basic checking to make sure the virtual address and the physical address, they actually match the information kept in this EPCM, the cache map. I'm going to skip some of the details of this thing, right? This is the process memory view. Okay. So we have the virtual memory space of a process, and part of the region is used for enclave. Right? So we have two kinds of code in the same application. Some code in enclave, some code outside. So they see different things. For the code outside the enclave, untrusted, okay, they see the regions. They have some region reserved by operating system, data, and the code, right? So this traditional one. The region reserved, the virtual space reserved for enclave, cannot be accessed by code outside of enclave. When they try to access this region, the virtual address space, the processor will raise exception. It will be aborted the access. But inside, if the code is inside the enclave, they can access everywhere. They can access the entire virtual memory space. But remember, the data outside of the enclave cannot be trusted. So when you develop the applications, develop code that runs in enclave, you have to keep this in mind. You can access everything, but remember you cannot trust the data you got from outside of the enclave. So the memory access is important, right? We can quickly look at this simplified process. So when there is a memory access request, we know that the Intel's processor will convert that into a linear address, combine the code segments and those things. We get the linear address is virtual address in Intel's processor. And then the processor will use the basically use the page table to convert the linear address to physical address. Just a traditional page table translation of addresses. Then after that, the processor was going to check whether this is access from enclave, from secure code. If it's not, okay, then go through the traditional way method of doing the access control and so on, right? If this is address, if it is access, okay, from enclave, and we'll check the target address to see whether the access can be granted or not. Right? You can see that it will check this whether the address, the targeted address, is in the protected memory region, and whether the physical address matches the virtual address and the physical address pair matches the cached information in those entries. If everything looks good, then the access is granted, and the access to that specific address can go ahead and get the data or write the data to the memory region. Otherwise, there will be a fault. The entire process is actually much more complicated than that because there are many things to check. But the basic idea is, okay, the processor will enforce this process at the access outside of the enclave. Code cannot access the protected memory region. So this is an extension of the processor. Right? There are 18 instructions in this extension. Some of them are used by like more privileged mode instructions code, and 5 of them are used by applications. If you want to write some enclave application, and you have some code and the data to protect. Those are the 5 instructions you can use. You can enter the enclave. You can exit from enclave. Remember, the enclave is a secure environment, and you can resume. You can get keys, and you can report. Report basically like betterment. Okay, you can report your sort of hash. Right? You can generally report the integrity. This is for the betterment. So you can use these 5 instructions. There are many data structures. Okay, we're not going to get into detail. Right? So the life cycle of enclave, right? How going to create and how the untrusted code can communicate with trusted code. Trusted code is in enclave, right? So the untrusted code will create You use those instructions to create enclave. Okay? After the enclave is created, the data and the code can be placed in the enclave. Okay? Then the untrusted code can call the trusted function. Okay? The call the trusted function and the control flow will transfer to trusted environment. And the trusted function will execute and prepare data and return the value to outside to untrusted functions. And then outside code can continue. So it's pretty much like system call. It's not simply a jump to an address. It goes through a set of checking, okay, context switching, get into the secure mode. Intel also have its own, provide some like services, right? Those code are in enclave that are created by Intel. Yeah. It has a launch in enclave, provisioning enclave, and quoting enclave. Quoting is the protected environment. So those are the enclaves provided, already like, placed inside the processor. Though they provide service to other enclaves. And when you write code that needs some enclaves, what you need to do is you partition the code into two parts. And it's something you don't, most of the code you don't need to protect. Okay. But there are some part of the code okay, will process secret data. And so those data and the code will be placed in the enclave, but you partition the code into different regions. Okay. And then you have the code, or you just use API to create enclave and load the data and the code into enclave, then you can call. One thing you need to remember that enclave, the code and the data are placed in the enclave by untrusted component, by application, by operating system. So as a result, you know that you do not want to put secret, hard code the key in the code or data you want to place in the enclave, because everyone can see that untrusted code or operating system can see that. Yeah. So what you want to do is you just have a pure code there, nothing secret. Okay. The code is not encrypted. Because if encrypted, it does not help you much because you need to get key to decrypt it. Right? The question is how to handle the key, right? You have to get into a secure environment to use the key. And so the code and the data to be placed in enclave are not encrypted, so everyone can change that. But later on, okay, you can check the integrity of the code. So you do not need to encrypt the code and do not hard code the secret in the code or data to be placed in enclave. Then you may ask, how does the code there in enclave get the secret, right? You get the secret later, okay, when you check the integrity of the code and data in enclave. Then you can communicate with them with the code there, instruction there. Then you can provide a secret. Okay, you can provide a key or a sealed key, okay, encrypted data to the function, those functions, and then okay, the code inside the enclave can decrypt, can process the data in clear. So the secret is provided later. But before you provide any secret to something in enclave, you have to make sure that is the enclave you created. Right? The code is written by you and it's running on the right platform. Okay, so you have the right enclave and right platform, then you can provide any secret data to the enclave. Yeah. So how do we do that? Remember attestation, okay, to prove that something is the correct software is running and the platform is correct. Right? So that's a similar idea. Since there are some keys involved in enclave, so uh, the secret can be sealed, can be protected by the key. The key can be used by code inside the enclave. Now we can go through the attestation and the sealing process. The idea is very similar to TPM. Okay. The question is how are we going to get the key. Right? Once you have the key, then it's relatively easy. Yeah. How does the code in enclave get the key, and how can it prove to other applications or servers that nothing bad has happened to the enclave? So there are two registers inside the processor. Um, One is called the register enclave. The other is register signer. Okay. So basically, the enclave register, this register is considered just a hash of the code. Okay, something you can the developer can compute outside and can be used as the identity of the enclave. The second one, the signer, basically is the identity of developer. So there are two registers inside the processor that can be used to prove to other parties this is the right enclave, the code and data. Probably you know that very often the hardest part of a system is to protect the key, right? So SGX have the capability of attestation and the sealing, and it needs key. Right? How the keys are generated and managed. In TPM, with TPM, you know that the keys are stored in flash ROM, right? So when BIOS boot up, it can get keys. But here, we assume outside the CPU, the data are not protected, cannot be trusted. Okay? So the keys have to be inside the processor. Okay? So with SGX, there are two keys inside the processor that fused, cannot be changed. One is for seal, the seal key, the other for provisioning. These are the keys in fused in the CPU. When you get a processor, the keys are already inside the processor, cannot be changed. So Intel placed the key there. Okay? And the users can, the enclave, the code inside the enclave can use this get key instruction, okay, to derive some keys from the information. Okay, on the slides you can see that there's what derived information based on the keys. Also has some current security versions. This is some code inside the processor has the security versions, and the measurement, basically the code you put in the enclave. This is part of the identity of the enclave. And the user, the owner, can also provide some random bits. Okay, so all the things will be mixed together, and when the user use these instructions, get some keys, and the processor will generate the keys, derive the keys, many different keys for seal, for report, and so on. Okay? So basically, the idea is the keys are derived inside the processor, and the code inside the enclave can get the key using instruction. So as for the two keys, important keys in the processor, the provisioning key and the seal key, right? They are placed inside the processor by Intel. That's why the assumed security parameter is the package. Okay, if you have the access inside the processor, then you know the key. Okay, so then there's no secret, right? There's another random information we mentioned earlier. Okay, all of the process can put some like a random information there. Yeah. So we have the keys, and how can we do the attestation? Okay, there are two kinds of attestation are supported. Yeah. So one is local. One is local. This is on two enclaves running on the same computer. Okay, inside the same processor. As different applications, they can do attestation. Okay. I'm going to not going to talk about the details. So basically, you have the one application has the one enclave A, another application have enclave B, and the enclave A can ask the processor to generate a report and send the report to enclave B. Enclave B can decrypt the report and know that this is another enclave I can trust. Okay, so this is local. So two enclaves running on the same processor. Okay. It also supports like remote attestation. There's another party not on the same computer. Okay. So you can consider this a scenario. You get a service from like a virtual machine provider, a cloud service. They have the server, but they use Intel's processor. Right? Now you want to check, make sure the enclave, the secure code, the code you're going to provide the secret key to, right? You want to make sure that enclave is running on the right platform. Right? Then you want to check, okay, do the remote attestation. So you are the challenger, and you have an application running in this virtual dashed box. So what you can do is you send the names over. You say, I want to check your integrity. The application you wrote will receive the request, will create the enclave, and the enclave will prepare the report, and the report will be transmitted to the application. Okay. But this is not done yet because this is like used some keys inside the enclave. You do not know the key, right? So the application will ask the processor, there's some code inside the processor to sign it. Okay, this is 4 and 5. Application will then ask this enclave provided by Intel to sign it. Yeah. Then the report was sent to the challenger. Yeah. Then the challenger can send this entire thing, okay, to a attestation server. Yeah. The server, you could create a server yourself, but typically people just send the server like provided by Intel. You see, whether this is something signed by your processor, by the processor you built. Right? So this is the whole process. So you send some names over, the application will use processor to generate some report, and you send the report to Intel server. Say, please check, make sure this, tell me whether this is a good report or not. Yeah. This is how you can do remote attestation. So with this feature, you can be sure that if the processor is not compromised, the processor is not compromised, then you can have some secret being processed, computed inside the enclave, and the service provider, say Amazon, will not know the data. So one of the keys, okay, get involved in this process is EPID. It is Enhanced Privacy Identifier. Basically, it's the processor ID, but it's better than the traditional one, the old one. So this mechanism is based on anonymous signature, group signature. So there are three keys. There's the issuing key and the verification key and a member key. Okay. The idea is we have group key signature scheme. So all the processors made by Intel is a member of this group. So any member in this group can sign something, but this is anonymous. So you cannot tell who signed that. You notice a member in this group signed it because we have a privacy issue. Right? So you know this is signed by a processor, but you don't know which one signed it. And Intel's attestation verification server can tell you whether this is a good signature or not. Right? So there's some crypto stuff involved, and you can check the signature, but you do not know who signed it. Yeah. So that's the like a crypto algorithm they use in this scheme. Yeah. As for the sealing, the idea is similar because you already have the key. You have a secret key. Then the enclave, the code running in enclave can get the key. Actually, only the code running on that in the enclave can get the key. Then the enclave, the code inside the enclave can use the key to do whatever encryption. You write the code, right? You can decide what algorithm you want to run. You just need to use the instruction to get the key. And the key is tied to the processor. So if you move enclave on another platform, then the key will be different because a lot of information will change, right? Or we know that the key derived from some keys provided by Intel burning inside the processor, right? So keys will be different even you run the same code on different processors. So enclave code can get some keys unique to the enclave and the platform. So the code inside enclave can use that secret to seal, to encrypt other keys or some confidential data. This is attestation and sealing. Yeah. So this is good, right? This is good. It can solve quite a bit of problems. You at least you know that in future you're not going to keep a physical computer in your garage. Actually, that might be less secure than get a server from Amazon. So this SGX. So what are the attacks on SGX? So the assumption of SGX is CPU is secure. If the processor is not secure, then the security assumption is not right, and then the nothing is secure with this mechanism. So most of the time, this too, CPU is secure. Okay? The attacks on SGX, the most common ones are side channel attacks, of course. Intel say we assume this is secure. Okay, we don't claim this is secure against side channel attacks. Most time, you don't have access to a processor. Also, very often, even if you have access to a processor, because the processor is so complicated, there's so many transistors. It's very hard to launch attacks on like high performance processor. Okay. Most of the attacks you see in the literature are on small processors, low end processors running like 100 megahertz. Then you can have something to do accurate measurement of the side channel information. It's really hard to launch like real side channel attacks on high performance processors. It's just too much noise. Yeah. But that people are trying. There's some result reported. So this side channel attack is potentially some way to break it into enclave. There are also like fault in hardware. Yes, operating system is complicated, so there could be bugs. Like a processor is also very complicated. It also have bugs. And a lot of things is happening inside the processor. For example, there's SMM, it's a system management module. Okay. This is runs at a lower level than hypervisor. People call it ring -2. So even like more privileged than hypervisor instructions. So that could be a bug there, but it's a simpler. But it could be. We don't know yet, but there could be, right? So 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 if that is broken, then of course the entire processor is not secure. So these are the okay, trend. The security analysis of SGX actually is still very active field. Lot of people in security community are still studying SGX and figure out whether they have another way to break into the processor. So this is Intel's method. AMD has its own thing. It's called AMD memory encryption. Okay. There are some papers talk about compare these two methods. And if you are interested, you can find out like do a simple Google search. Just SGX versus AMD memory encryption. You can find tons of pages. I think that would be like short session on SGX. Okay, I think if by now, okay, when we talk about security of application, security of operating system, the booting process, the processor. Now we talk about the inside the processor, the SGX. Right? So we covered the privilege level from ring 3 to ring 0, -1, and now -2. I briefly talk about ring -2. I think that would be the nice ending for the course. You know, the security of a computer like span many levels. Okay. Now, probably this will be the last question, right? So what have we learned in this semester? What do you remember? Just quick review, think about what we have learned in this semester. Okay, without like preparing for exams, right? So there are some common, like I would say, as students in security concentration, you should have something in your head and you can talk about security stuff. Okay, string copy is bad. Okay. But some people, some students already know that. All right, so in 3100, string copy is bad. Okay. Actually, people try to fix the string copy, right? But they have a string encopy. uh, string n copies actually it's not that good. Lab 3, okay, lab 3. Yeah, lab 3 is the implementation. Yeah, as I mentioned earlier, we have done a lot of attacks, but we have not really had a lot of project on the design of system, put the design in like incorporate the security mechanisms or whatever features you learned in project. So not only okay, you need to know where the weakness is. You need to know how to do things properly. Okay, of course, okay, the things you learned nowadays may not be the best practice. Okay, may not be the best way to do things in 5 years, 10 years. Things will change, right? But that's why you need to keep learning. You know what's going on and what are the most recent attacks and what are the countermeasures and the things you can do to to like prevent those attacks. Mm. Anything? I think buffer overflow things. The project may not be very helpful, right? Some students already took 3140, so probably going to think about some other things related to buffer overflow because um, as you know, the attacks have been there for many years, for decades, but we still have the buffer overflow like vulnerabilities. So it's still important for students, for future engineers to know that they can be very careful with buffers. Anything. Okay, so access control. Okay. Yeah, for access control, actually, I think we should teach that like access control on Windows and Linux, the basic concept. We should teach that in freshman courses. Right? Um, but as the construction of the curriculum, we don't have we don't have a good places to teach like access control of file systems. At least you learn, right? So before you graduate. Yeah. I I th- I think it will be good if we can if we can see more seniors taking this course at the end of the junior year, so they could use something they learn in this course in senior design. Okay, yeah. So yeah, this is a more practical courses. Because not everyone, I think most people will not work on crypto, will not design algorithm to do mathematical analysis of the protocols and algorithms. They're going to use the algorithms. And actually, a lot of the practices in engineers are not really closely related to crypto. It's about how you use crypto and some other stuff like to how do you enforce access control, how do you define security policy. Any other things you can think of? Okay, I think a side channel could be new to many of you. Very often, software developers may make silly mistakes. Could be they have other things to focus on in the project, or they just tired at that moment because they worked overnight and by silly tiny mistakes at 5 a.m. in the morning. Uh, yeah, uh, but and this, okay, the potential attacks, and mm, you avoid the like obvious mistakes. And the risk control. Okay, we see that a lot of attacks, because of the risk condition. Uh, the risk condition. Uh, 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 okay. Wait, I think we talk attacks on in SSL. Okay. Uh, God, it's bleed heart, something like that. It's uh, the HSS buffer overflow. The 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 bug was introduced in code in early morning, and the developers was really tired at that time. Okay, so just too lazy to do it like a check on the bounds. Anything else? I hope you understand the booting process better, and you can do some troubleshooting. If you have requests from your friends or your family members, you understand the big pictures and how computers uh, how computers boot nowadays. Okay, I think we have only 15 minutes. I just checked the set response rate on in the system. Only six students responded. Okay, so I think we can stop the session now, and I give you some time to complete the survey, and not just that survey. I think most of you already uh, received many emails from Joy about the exit survey. So for graduating seniors, so the department also would like to uh, get your feedback on the curriculum, your experience at UConn. Okay, so if you haven't, please complete that survey too. So I'm giving you like 15 minutes to complete both, and should relatively be easy. Okay. If you have any questions, you can, okay, or how to find me. Okay, my email has been there for years, haven't changed. So if you want to contact me, ask any questions, or discuss anything, great ideas you have, you're welcome to do so. Yeah. Even after you graduate. Okay. We want to keep in touch with alumni, but it's very often we send them email and they don't respond. Okay, just like the exit survey. Okay. But still, I think we have like 20-25% of students who have not responded yet. Okay, so I'm going to stop now, and hopefully you complete the surveys, and congratulations to seniors. Okay, I can say you made it, right? And I'll see some of you, some juniors next semester on campus. Thank you, and have a great semester. The great remaining 3 weeks, 2 weeks that you come.